Okay, welcome back, ladies and gentlemen, to Mr. Duran's physics course. And I want to begin today's lesson dealing with the concept of relativity. And I'm sure that when you think of the term relativity, what might come to mind is maybe the formula E equals mc squared, or that of the person who figured it out, Albert Einstein. Now, those are great things to think about. However, oftentimes the term relativity and that formula eludes us still. We still don't quite understand what that means. And so I kind of want to hope that we can figure out a way to understand how he came up with that process, and also help us figure out how he came up with this fundamental property of the universe. So let's first take a look at a couple of situations here. Here's situation A. There's a gentleman, he's on a flatbed truck, it's not moving, and he throws a ball up and down. Now, to his perspective, that ball goes up and back down, and it follows the laws of physics as we know it. However, if we have a different situation, with situation B, we have a very similar gentleman or woman, and they're on a moving flatbed truck. Now, to their perspective, they throw that ball up and down, it returns to them just as they normally would. It follows the laws of physics. However, if you're looking at it from an outside perspective, that ball does not go straight up and down. It actually follows a parabolic path that coincides with the forward motion of the vehicle. So in measuring the distance traveled by the ball, who's right and who's wrong? I want you to ponder on that as I show you another little piece of paper here that might give you an idea of what relativity may be. When you are standing on a corner and a car flies by, to you, that car is moving and you are sitting still. We can't forget that we're also using the Earth itself as a reference point. So let's imagine this situation happening in space. You are in space floating and you see a vehicle float by. There's nothing else to refer to, just you and the vehicle. It would seem that the vehicle is moving. However, if you were floating in space and you were instead inside the car, from your perspective, it's the person that's flying by, not the car itself. So again, I ask, who's right and who's wrong? These are all terms I want you to think about, or situations I want you to think about in terms of physics and relativity. Now think about this. Whether sitting still or in constant motion, the laws of physics are consistent for all non-accelerated frames of reference. This is to say that back in our flatbed situation, that if that gentleman was trying to measure the acceleration of that ball up and down on the flatbed, whether it's moving or not, it would be the same. So the laws of physics are consistent whether he's moving or not. Okay, let's keep that in mind because that's the first postulate that Einstein used to help figure out relativity. Here's a small situation that might help give you an understanding of how that might be changed, though. In this situation here, I have a gentleman, let's call him the observer. And the observer is watching two people throw a ball. Let's call the guy in the plane A and the guy on the ground B. Now, from both their perspectives, they're throwing their ball at 10 meters per second. However, the guy in the plane is traveling at 230 meters per second. Now, he would say his ball is traveling 10 meters per second. He would say his ball is traveling 10 meters per second. But what would he say? Now, we know that in terms of vectors, and we're using the Earth as a reference point, in this guy's situation, he would look at situation A and say, oh, that guy, the ball is traveling 240 meters per second, whereas this guy is traveling at 10 meters per second. But who's the actual observer here? Who's the one who gets to claim what is actually occurring? So this is the first situation I want you to think about, because this ball is traveling a specific speed, but it's observed at different speeds. Now, there is a different fundamental, behavior of the universe, and that is of the speed of light. This ball, its velocity varies. However, the velocity of light, it doesn't vary. And to all observers, and for all frames of reference, the speed of light is constant and thus unchanged by motion. That means that no matter if the plane is moving or not, that every observer who looks at light will measure it at the same velocity, which is at 3.0 times 10 to the 8th meters per second. So here's another situation. Instead of a ball being thrown, here is a gentleman with a, let's call it a laser, on an airplane, and a gentleman on the ground with a laser. From his perspective, the ball is traveling 3.0 times 10 to the 8th, and from his perspective, the light beam is also following the same velocity. What does this guy see? Well, based on the physical, I guess you call it a law, or just a fundamental property of the universe we realized, is that the light, for all observers, goes at that speed. So he sees it at 3.0 times 10 to the 8th meters per second for both people. How can that be? And what does that mean? Ponder that idea. How could that possibly be real? We know the laws of physics and vectors and situations, so why does it seem that way? So I want you to assume those two postulates to be true, though. And I want you to consider the following situation. Let's imagine that there is a huge cosmic mirror up in space. And it is 1.5 times 10 to the 8th meters away. So I would assume that if light travels 3.0 times 10 to the 8th meters per second, that it could actually travel up and back in that 1 second. So if we were sitting still, the light beam would go up and come back in 1 second. However, if we were moving, from the perspective of the guy in the plane, yes, it did go up and down because the plane is moving as the light beam moves upward. However, the path that light beam takes is longer. Now let's remember, from the perspective of the person in the plane, the light beam did the same thing. It went straight up and went right back down. However, from the outside perspective, the light beam did not go straight up and down. It went over, across, and back down. Now, if this observer saw it go up and down in 1 second, and same with the person who was moving, how can an object have the same velocity but travel in the same time? Or how can it go a further distance and travel in the same time? Consider that situation. When you come to my next video, I want to show you how there's a situation here that doesn't quite mix with this whole perspective here. And maybe it will help change your perspective of the way the universe works. Thank you.